let us continue our discussion on counting DFAs. We looked at this example wherein we were counting number of DFAs possible from this on sigma equals 0. Okay, and to do this counting we looked at how many functions are possible from q cross sigma to q, and we know that each element in this, like q0 comma this or q1 comma 0, and they map to q0 or q0 comma 0, q1 comma 0, and they map to q1, or q0 comma 0 is mapping to q0 and q1 comma 0 is mapping to q1, and another function is q0 comma 0 is mapping to q1, q0 comma q1 comma 0 is mapping to q0. Then we said you just focus on one function. This function itself can give you some number of DFAs. Okay, so we said you look at the underlying transition diagram. Say q0 comma 0 is q0 and q1 comma 0 is q0. So in this can be a start state or this can be a start state. So which means we get two more automatons. In one you get q0 as the start state and another one q1 as a start state. And suppose consider the automaton in which q0 is the start state. Then there are possibilities for final state. For example, none of them are final states, that's one, and other thing is final state is empty, or q0 is your final state, or q1 is your final state, or both are final states. So which means the function f1 itself gives you two automatons and one for each, with q0 being the start state and q1 being the start state. Subsequently, this q0, with q0 being the start state, we get four different DFAs. In the first one there is no final state, in the second one q0 is the final state, and so on. So which means even with this you get another 4, which means the function f1 is giving 8 different DFAs, correct? Now with this we get two more, with q0 being start state 1 DFA and q1 being start state another DFA. With q0 being the start state, we look at possible values for final states, we get 4 of them, and similarly this gives us 4, which means this function gives us 8 different DFAs and they are all distinct. And similarly this will give another 8, this will give another 8, this will give another 8, so there are 32 DFAs. And we also observed that number of functions is 2 to the power 2 into 1, and that into possible values for start states is 2, the cardinality of q, and that into possibilities for final states 2 square, that gives you this number. Now let's see, can we generalize this for other values of q, sigma, and so on. Let's consider one more example. Say let's look at q0 to be q to be q0 q1 and sigma to be 0 1. So now for this, if you look at the number of functions q cross sigma to q, you get to see that cardinality of this one is 2 and cardinality of this one is 2 and cardinality of this one is 2, which means how many functions are there from a set of size 4 to a set of size 2. So number of functions is 2 to the power 4, so 16 functions are possible. So take one function. So take a function in which q naught on 0. So here you will have entries like this, right? Q naught comma 0, q naught comma 1 and q1 comma 0, q1 comma 1. And if you look at this, let's assume these two are mapping to 0 and these two are mapping to 1. So the elements in the domain are the elements of this cross product q0 comma 0, q0 comma 1. So there will be 4 elements and they map to 2 elements and q0 and q1. Okay, let's assume these two are mapping to q0 and these two are mapping to q1. But there are many functions, there are 16 of them. I'm just focusing on this function. Now in this function, from this function we get 2 DFAs. So we get one in which q0 is the start state, the other one you start at q1. Okay, very similar to what we did here. So each element in q is the candidate for the start state. Now with q0 being the start state, we look at possible values for the final states. So it could be empty, it could be q0, it could be q1 or q0 q1, which means we get 4 DFAs with q0 being the start state, with another 4 DFAs with q1 being the start state. So we get 8 DFAs for F1. So now how many functions are there? So number of functions is 16, therefore number of DFAs is, for one function it is 8, for 16 functions it is 16 into 8. So we get this many DFAs. Okay, but how do we arrive at this number? The number of functions is 2 power 4 and possible values for start state is 2 and possible values for final states is 2 square. So we get 2 power 7, which is 128. So we get 128 different DFAs for this example. Okay, so now that we have seen the picture with respect to 2 examples, let's look at the count for arbitrary values of q sigma, and with that what count we get, let's discuss. So now given q set of states, say q0, q1 and say qn, and sigma consists of some symbols, let me say a1, a2, ak, not necessarily 0, 1. We can have any number of symbols, 0, 1, 2, dollar, things like that. So what is that we are interested in? We are interested in counting number of DFAs. The first counting, just like the way we did counting for those 2 examples, let's build on the similar line. First count how many functions are there from q cross sigma to q. So cardinality of this is n, and cardinality of this is k. Cardinality of this one is n. So number of functions from a set of size nk to a set of size this. So number of functions is n to the power nk. Then if we fix a function, then such a function can give how many automatons? It can give first automaton in which, okay, it is q0 to qn. So let's start with q1 so that the counting is correct. So otherwise the size of q will be n plus 1. Let's assume q is q1 to qn, so that the cardinality of this is n and sigma is k. Okay, so what all functions we can get? We will get an automaton in which q1 is the start state and q2 is the start state, and so on up to q1 is the start state. So if you fix a function, we get n different automatons. In the first one, q1 is the start state. In the second one, q2 is the start state. In the nth one, qn is the start state. For an automaton, we can have only one start state, but many final states. So which means each of them can give you n more. Then with q1 as the start state, what all automatons one can get? You can get an automaton in which this empty set is your final state, which means no final states at all. And then q0 is your final state, then q1, then q0, q1, like that. All subsets of q are possible. So with q0, with q1 as the start state, again I'm sorry, q1 as the final state, then q1, q2, because we start from q1. So now we see that we get 2 power q automatons. Okay, so if you fix a function, that can give you n different automatons. In the first one, q1 is the start state. In the second one, q2 is the start state. So on up to q1 is the start state. If you fix the first automaton in which q1 is the start state, that can give you 2 power q automatons, depending upon whether phi is the final state or q1 is the final state, and so on. Okay, so for one function we get this many. So for one function, and with q1 as the start state, we get this. With again q2 as the start state, we get this. So for one function, so possible values for start state is n. Possible values for final states is 2 power cardinality of q, which means 2 power n. So which means how many DFAs are possible? Number of DFAs is number of functions. Number of functions is n to the power nk, and for each of them the possible values for the start states are this, and for each of them possible values for final states are precisely this. So in general, you look at cardinality of q to the power cardinality of q cross sigma times cardinality of q start state times 2 power cardinality of q for the final states. So this is precisely our count. So the number of DFAs possible from a set q and to again q. When I say q on sigma, okay. So you have n states and k symbols. First you look at the possible functions, then look at possible values for the start state, and fixing the start state, count how many automatons are possible for various values of final states. That will tell you the overall count, which is precisely this number. Fine.